So here we are in office hours again. We're going to talk about some lab things, what it means by a buffer, what pKa is. We got one A post-lab question. I want to talk about the caption and title a little bit as well. All of you have had terrible titles so far. Talk about why I feel that way, in my opinion, I should say. And then we've got some questions from the homework problems as well. Okay, so buffer we talked about. I think we're all okay with that now. That's the HPO4 minus 2 minus to the H2PO4 minus. This is our that ratio is called our conjugate ratio, and then we can have Ka is equal to that ratio, HPO4, sorry, this should be concentrations as well, 2 minus H2PO4 minus times H plus. Right, and so whenever it's talking about a buffer, it's really talking about the ratio that we're controlling here. Now, we didn't really do much to control that ratio in the experiment. We just approximately mixed these two things together, and then we measured the H plus. And so we learned more about how to do those calculations yesterday in class, where I can just call this thing like the ratio number, and this whole thing becomes like Ka equals some ratio times H plus concentration, right? And then we're just solving for the ratio, whatever ratio we made, or we get the H plus and we just measure the H plus. The other interesting thing we can do, because we don't measure the H plus, we measure the pH, we can also go ahead and just take the negative log of this thing, and we can say negative log of Ka is equal to negative log of ratio times H plus. And then we can do a little bit of rearrangement if we know how the logarithm works. We can call this negative log of Ka equals negative log of ratio plus negative log of H plus. And the reason that people like to do it this way, even though it's a little bit weird, is we know that the negative log of H plus, this whole thing is just pH. And then this whole thing, this is where pKa comes in. This whole thing, negative log of Ka, that's pKa. And so then, last thing we can write down is I can subtract that over, and I can say pKa minus pH is equal to the negative log of whatever my ratio is. So I can essentially, there's a couple different things we can do. If I know the pH and the ratio, I can figure out the pKa. If I know the pKa and the pH, I can figure out the ratio. If I know the pKa and the ratio, I can figure out the pH. So depending on which variables we know and which variables we don't know, we can solve for the other thing.
Wait, so is the ratio the concentration of IND and HIND, or what's
so right now I've got it written down. We can do it as many different things. So right now I'm doing it for the buffer system. So that's our H2PO4 or HPO4. But we can also do it for the indicator system, right? If we're doing, whoa, it's my first time using a new pen in a while. If we wanted to do it for the indicator system, right, this type of logic works for any conjugate pair, any weak acid with its common ion. So I can do that for the indicator system, and it would look exactly the same. It would look like pKa minus pH equals negative log of ratio. But in this case, my ratio would be IND minus over H IND. And this is part of what's obscured in the lab that we didn't really talk about, is you actually kind of have two acid-base systems going on, right? We've got our indicator system that we're trying to control, and then we've got a buffer system we're using to control it, right? So when we measure, we use the conjugate ratio. We don't do anything with the buffer besides force it to be a particular pH. And then once we have this pH, we can plug it in here, and now we know the pH. We can measure the rest of the ratio, and we can solve for the pKa. Again, this is kind of several steps. This was so I could show you what pKa is. It also gives us this idea of like what's the range of possibility, right? This ratio can't go all the way from 0 to infinity. There's places where the x is small approximation will stop working. So it's just a little range around that pKa value. I find it easier at the level we're doing to think about it like this. Right, kind of the starting point before we do all the manipulations. It's easier for me to think about it like this. If you take bio classes, or if you take environmental science classes, or I think there's some materials classes in the upper division stuff where you worry about controlling the pH, you'll start to recognize this as the buffer equation, also called the Henderson-Hasselbalch equation. We're not going too deep into it. We're really just working with this equilibrium expression. But the whole idea of pKa is this idea is like you can think about pKa as it relates to pH. It just makes the numbers easier, right? It's like an acid has a pKa of 4.74. That means it's going to have a buffer. It can act like a buffer around 4.74. It gives us this easy way to characterize the acid system. Rather than saying 1.8 times 10 to the minus 5 for its Ka, we can just say pKa is 4.74. Yeah.
What's the use of splitting up the ratio and the H plus? Because like in the end, don't you just get the same answer?
Yeah, for us we do at the level we're doing now. Yes. Later on, and this is a next quarter problem if you're taking chemistry next quarter. Next quarter, we are specifically controlling that ratio to get buffers at particular pHs. And the amount of the weak acid and its conjugate ion, or its common ion, conjugate pair, that has to do with some other properties of the buffer, right? In class the other day, I said buffers resist change to pH, but not infinitely. And depending on the concentrations and volumes, we can get what's called a buffer capacity. But those are problems for not this class. Come on in, you can take this chair if you want. So those are problems for later classes. But those things, this, like I said, this is kind of going a little bit extra. This is fine for us this quarter. Also, like, just in case other people show up, try to keep bags tucked under like chairs and desks and things like that.
I just saw it came from my exam.
Oh yeah. Let's go ahead and look at post-lab question 1A. Okay, I'm going to erase the board. Any questions about this before I erase? Okay, let's look at 1A, and then we'll talk more about graphs, particularly captions and things like that. This is my pocket. Oh. Okay, so we are looking at this is so weird. We've got so many new things today. Wow. Just for comparison, this is the pen I've been using for like probably 5 years. And this is the brand new one. Like, it's like it's a little softer. Also, like this one like clicks again. Well, it doesn't matter. It doesn't matter. Okay, let's do the problem. Can you go ahead and read the problem to me?
Yeah. Given the equilibrium SO2 Cl2 goes to SO2 gas plus Cl2 gas, and then the Kp equals 2.4 at 100 degrees Celsius. It says determine if this reaction is at equilibrium under the following conditions, and specify or state which direction the reaction will proceed to reach equilibrium. Okay. And then it gives you like PSO2Cl2 equals 0.568.
0.568?
Yeah, ATM. And then PSO2 equals 0.125 ATM. and then PCl2 equals 0.5 ATM. And then you have to choose between left at equilibrium or right.
Okay, so to get this started, we don't know if we're at the equilibrium. We've got these kind of initial conditions. So if we're looking at initial conditions, what are we going to calculate?
Change? Or
Before the change?
Oh, the Q?
Yeah, we're just going to calculate the Q. Here's the weird part. Okay, never mind. I'm being weirded out by my new pen. So we're going to do Q, and we're going to do products over reactants. Since it's talking about it in pressures, I'm just going to do the pressure of SO2 times the pressure of Cl2. It's all 1-to-1 mole ratio, divided by the pressure, products over reactants pressure of SO2. Ooh, I made that Cl2 big. Cl2. So I can calculate that is going to be 0.125 times 0.5 divided by 0.568. And I can tell this is going to be less than the Q is going to be less than Kp. Oh, I switched my caps. That's why this cap's not working. There we go. Okay, so we go ahead and calculate 0.125 times 0.5 divided by 0.568, and we get 1.1. So I've got this situation where my K is bigger than my Q. Do we know what it means when the K is bigger than the Q?
Doesn't it go towards product?
Yeah. Right, so I'll show you a couple things real quick. Right, so the first way we can think about it is I think about this in terms of products over reactants. I'll call it products initial over reactants initial versus products at equilibrium over reactants at equilibrium. And because I'm terrible at fractions, I usually just think about the top, the numerator, and I say, look, in this situation, I don't have enough products because my products number is smaller. So I must need more products. The other cool trick, and we can do that logic for each thing, the other thing is if you set it up so KEQ is first, the greater than makes a little like arrow pointing that direction. Less than makes an arrow pointing that direction. And it makes it so I don't, because like, honestly, even with the number of years I've done this, I always have to, if I don't do this trick, it takes me just an extra like 15, 20 seconds each time that I'm thinking about this, because I go, products of this, products of that, it goes that way, okay, it's going to go towards products. Whereas like, if I just do this, KQ is bigger than Q, I can just immediately see it. It's a nice little shortcut.
Can
And
you
if it's
explain
equal.
again? Sorry.
So the full logic or just the picture?
Just the picture.
Picture is if KEQ is first and it's bigger than Q, the greater than sign makes like an arrow pointing the direction the reaction goes, so it's going towards products.
Oh, I get it. Okay,
Right, and the
that's
less
cool.
than makes an arrow pointing towards
That's a good trick.
reactants.
I'll
So
put that in my notes.
yeah, it just with the number of times I do problems like this because of how often I teach this class and the next quarter class, having that little trick just makes it so it's just a little bit faster each time. It's probably saved me hours of my life over the course of me doing it. And for all of you, when you're like doing an exam and you're like, God, every second matters, saving you 10, 20 seconds of like slowly thinking about it feels good. So that's 1A. Any questions? That's all it asks, right?
Yeah.
And so each problem is kind of like that. Calculate a Q and then do a comparison. Eventually, you also have to make a caption and a title. So, are we ready to talk about that? Okay. So we want to start thinking about what professional kind of titles and graphs and things would look like. So, if we make a graph, we of course want titles. Right, so we have absorption with no units, we get a concentration and molarity. It might be nice to do concentration and micromolarity. So the answer is like 6, 7, 8, 10, 12, rather than 6 times 10 to the minus 5, 7 times 10 to the minus, or 6 times 10 to the minus 6, you know, those smaller numbers. We get a series of dots. We get a linear fit. We get a line for it. We get an r squared. We usually like to have the r squared on there as well. I'll say mine is 0.987. We can talk about what that means. The worst title you can give this is the title that most of you were told to give it in high school, which is right, absorption versus concentration, dependent versus independent, right? Why is that a bad title?
Doesn't tell you anything new.
I already see that, and I already got my labels. It's not new information. It's just like I'm repeating stuff that's already there. Everything we put on the graph, we want it to be useful, insightful information. So a lot of times we don't do, in professional settings, we actually don't do graph titles at all anymore. We just do captions because we want to have more information. So we create a caption. We don't really do titles at all because you can't put enough information in the title to make it useful. So you make a caption, and your caption really wants to address a couple things. Your caption can be kind of like 3 or 4 sentences long, actually. It can be, captions get really long. I can pull up some journal articles and show you like captions that are like really long. Let's see here. Those are really old. But like so here's a figure, there's the caption. Right? So captions can get really lengthy. That's the caption for this one figure. Here's the caption. I guess this is all caption for that figure, that pair of figures. Okay, so captions can get really long. And that's because captions are supposed to provide useful, complete information. So ideally, what you want to think about for your caption is, if I dropped this graph looking just like this, would someone be able to pick it up and figure out what I was doing? Would they be like, oh, this belongs in someone's Chem125 class? Or would they be like, I have no idea what this is? Right, so our caption kind of wants to address a couple different things. What is the figure? So this is the standard curve for acidic conditions, parentheses yellow. I don't know if it's yellow or blue, right? Standard curve for acidic conditions, parentheses yellow, of bromothiamyl blue. I can't remember what indicator for an unknown indicator. I don't think we knew the indicator. It was like an unknown indicator. For an unknown indicator that has an unknown indicator. I'm going to add something here. Right, and so that's what it is, right? And that would be fine. Like when most people think of a title, they're just thinking of the what. So that sentence would be almost reasonable, kind of unreasonable title, right? But that's what the title would be. It would be that much. It takes that much to be useful. You might even include recorded at lambda max equals 620 nanometers, right? All of that information, because if someone was going to recreate this, they'd need all that information. Then we've got our why how, which is a series of 4 solutions made by at various concentrations with absorbances measured using a standard classroom spec viz. If we were trying to be really professional, we'd include like the model number of the spectrometer we're using or something like that. In order to characterize, like, and then you can have your why, how, and then your result is, in this situation, we might not do a result on these since it's in a lab activity where the result is like the next box down. But if this was in a scientific journal, something like that, you might also say, this gives us information that's useful because of blah, right? Like this allowed us to determine this information about this other thing that we're doing. In the lab activity, results is kind of the next box down. So we at least want like a what and why, how. Most people, if you just get a what, that's going to be good enough. Like the fact that it says standard absorption curve for an unknown indicator in acidic conditions, the series of dilute solutions starting with a stock of 80 micromolarity. Right? The idea is that if someone picked up this figure with a really nice caption, they could look at it and be like, oh, I could recreate this figure. I know what they did, I know how they did it, I know where they did it, and if I went and got those supplies, I could make the same figure as them. So that's the kind of mentality you want to have as you're putting your caption in. Most people don't do that. And again, freshman class, right, a lot of your sophomores, we're just getting used to this. By the time you're seniors, you're going to write enough like captions and explanations for things like this that you'll be like, oh yeah, of course. You'll look at, like, I encourage you to come in your like senior year, come by one of my like 124, 127 classes and like be like, was I this bad? And you're like, there's a lot of growth that happens, like academically speaking, in the next few years. It's really, you don't notice it when it happens day after day, but if you come and talk to, like, if you come to one of my classes your senior year, you'll be like, this class is way easier than I remember. Guarantee you. You might still have memories of not liking it, but you'll look at it and be like, this is easy. Questions about that? Let's go ahead and move on to 6.1, 7.1, and I'll tell you this story. I don't really need to record this, but I'm going to anyway. You can see. Come on in, you can take this chair. I was teaching a freshman class. It was Chem125. It was fall quarter, and the class was like 75-80% freshmen, so it was their first college class. And the students, this was a couple years ago, the students were like really salty. It was mostly engineers that got a block schedule into it. They all were like really upset. They're like, we don't like chemistry, we don't want to take this, we were block scheduled into it, we don't even know why we're taking it. And for some reason, there were like 3 seniors and a junior that were friends that were retaking the course. And they all sat at a cluster in the back. And like the students would complain about something, and like I was really glad that they did this. And they were kind of like mentoring people around them. They're like, no, that's easy, like you're just gonna be way harder in another year. And they'd be like, we'd be doing something with like crystal structures, and they'd be like, why are we doing this? And they'd be like, mate 353, you're gonna need to know this stuff, learn it now. Because like they were just like, no, all this stuff comes back, all this stuff comes back. Come on in, if you're okay sitting on the floor, there's space up here. And so it was just really funny and like being like, oh yeah, okay, I get skewed because I talk to freshmen all the time, like really often, and it was really nice to have seniors in there being like, nope, that's not how it is. Like I had students complaining about not knowing when my due dates were, and they were like, it's literally on the website every day. Like other classes, your senior classes, you got to figure it out on your own. And it was just nice to have people who are like, oh okay, yeah. I'm trying to set you up for success. And all of them got like A's and B's, and all of their friends were like, how'd you do, like all of the other students in the class were like, how'd you do that? And they're like, you just study. But the thing is, by the time you hit your junior, senior year, your study habits have changed, your study expectations have changed, like the way you engage with like your curriculum, your content changes. Because a lot of people coming in, even like by the end of your freshman year, you haven't like totally shifted. Because there's a lot of sophomores in our classes, right? But you're starting to realize, I think, that the things that were successful for you in high school are not as successful in college. And you're starting to be like, oh, and so by your junior, senior year, you've got these new successful skills. And then once you graduate, you got to go get new successful skills for whatever your job is after this. Okay, sorry for the sidetrack. Let's go ahead. We've got some questions from 6.1 from stuff in the past. So we're going to look at number 13 and 23. Then we're going to do 7.1, number 1 and 9. If people want to add more questions to these, we can. And if you got specific questions about the lab, after we do these 4, I can do particular like help. Did yours work yet? Okay, cool. We can do like troubleshooting. I'll pause the video. I'm recording, by the way. I'll pause the recording and I can do individual help for different lab issues. So let's start with 6.1. Number 13.
For the lab, is the like original like Hinge stock solution concentration the same for the yellow and the blue? Because I just did the blue.
It is.
But I'm getting the wrong answer, so I don't understand. Like.
Let me do
Okay,
these
yeah.
and then we'll come look at it.
Okay.
Double check your concentration calculations because the volumes weren't the same.
Yeah, the volumes of the yellow were 3, 4, 5, and 6.
Yeah. So you got your different concentrations, but your same stock concentration. We'll look at it in a moment. Who's got number 13 ready for me? Yeah.
I do. Let me read it to you.
This is one of the ones that changes values too, so we might all have different. It's the one of the ones that changes values, so we might all have different.
You might all have different, but we're just going to do one example, and then everyone should be able to kind of like use that as a framework for how they approach. Yeah.
Alright, so calculate the value of delta G of reaction for this reaction at 25 degrees Celsius when the concentration of lead ions is 85 micromolar and the concentration of chloride ions is 27 micromolar. Given the KEQ is 1.6 times 10 to the negative 5.
What was the lead concentration?
85 micromolar. And then it's 1.6 times 10 to the negative 5 is the KEQ at 25 degrees Celsius. And then the equation...
1.6 times 10 to the negative
5. And then the equation is PbCl2 solid goes back and forth with Pb2 plus aqueous plus 2Cl minus aqueous.
Perfect. So this is delta G, not delta G standard. So if we remember, delta G standard is negative RT ln KEQ. So I just take my KEQ value, plug it in for my temperature, I can solve. Delta G is going to be RT, no negative, natural log of Q over KEQ. Right, it's got this comparison of where am I versus where am I going. So I say, okay, where am I going? I have to calculate my Q value. My Q is going to be my lead concentration times my chloride concentration squared, which is going to be 85 times 10 to the minus 6 times, whoa, these are really small values, 27 times 10 to the minus 6 squared. This is going to be crazy product favor, or this is going to go crazy towards products, because these are such small values. I get my Q value using a calculator. Ooh, oh no, these are right. Oh, let's do the 27. 27 times 10 to the minus 6 squared times 85 times 10 to the minus 6.
Oh, do you not need to do 2 times 27 times 10 to the minus 6?
No. Right, because it's giving me the chloride concentration without any change step. Is that what it was?
That's why I kept getting
Yeah. So the 2 only comes in place when we're actually doing something stoichiometric. Right? So if I started with solid lead and then it dissolved into chloride, or if I was dissolving something like, I gotta think of some chloride compound that's really soluble. If I was doing some solubility of some soluble chloride compound, sodium chloride, but that's a 1-to-1. I was trying to think of something that's a 2-to-1. Magnesium chloride, right? If we were doing magnesium chloride, then we'd have the 2-to-1 in there. So if this was if it was 27 micromolarity magnesium chloride, the part that would be important is that there's 2 chlorides for every magnesium, and that would cause the doubling. But since it just gives us the chloride concentration already, it's giving us the initial. So if we looked at this in a table form, right, we'd have PbCl2, I've got it up there, solid, going to Pb2 plus 2 Cl minus. My concentration here is 27 micromolarity. The plus 2 is going to come in down here. That's where the 2 is when we're actually thinking about the stoichiometry. We don't double the first thing, that's just initial. Let's go ahead and finish the problem still, even though we found the potential mistake. So we've got our Q value here is 6.197 times 10 to the minus 14. And then we just plug everything in. I'm going to have R, which is 8.314. What was the temperature?
25 degrees Celsius.
So we'll call it 298 times natural log of, I'm just going to call it 6.2 10 minus 14 divided by 1.6 10 minus 5. Right, and I just calculate that. I should find that it's a negative value, meaning that it's spontaneous. Divided by 1.6.
I think I was also kind of wrong because it said it was at 25 degrees. So I was like, shouldn't like it be delta G standard? Because like shouldn't it wouldn't it be 0? Because at delta G or like at standard delta G is like 0.
Remember, standard is not just
Or like
the
at
temperature
82.
and pressure, right? So standard is not just the temperature and pressure. Standard is also the concentrations. So standard is also the concentrations. Take the natural
So
out
what
of
does
that.
that mean? Like also concentrations. Like there's a standard concentration number.
Yeah. Right, so I'm getting a negative 4.79, 47.9 kilojoules. Where's that in joules? Oh yeah, that's in joules and I'm switching it. 47.9 kilojoules. Right, so I'm getting a really large negative number, which means that it's going to be spontaneous, which means it's going to go towards products.
What's the difference between G and G standard?
So notice at G standard, there's a couple different things. The main thing is G standard is this idea of how there's the technically correct and the kind of the practical use of it. The technical correct is G standard is a measure of standard states. So G standard technically comes from this idea of like sum of delta G standard formation of products minus, and that thing. But the place where it's useful is at standard conditions, Q is equal to 1, right? Because standard conditions are 25 degrees Celsius, 1 atmospheric pressure, and concentrations equal to 1 molarity. See ya. So in this situation, when we're at standard conditions, right, delta G is measured from any point to the equilibrium, so it's kind of doing a slope idea. Whereas delta G standard is essentially being measured from a specific spot on the curve.
So standard is for more application versus...
Yeah.
Okay.
So standard gives us, essentially standard just gives us a way to like talk about like things from an absolute position, right? So if you were talking about delta G, it's like, well, delta G for which point on the curve? Where standard says we're always going to look from the same spots. Okay. We good for number 13? Let's go ahead and look at number 23. This was a question from yesterday that I didn't get to, also on 6.1. And then we'll move on to the 7.1s. No questions on 6.2. It was pretty straightforward. Or hasn't been done yet. That's also okay. 6.2 is supposed to be mostly review, so it should be fine.
For 7.2, are we expected to be able to do that yet? That's the voltaic cell notation and potential one.
We've started it. We're gonna hit it kind of first thing on it tomorrow.
Okay, so after that we should be able to do MQs. Okay.
Yeah. And we started with the way that I drew the cathode and the anode. We're starting to get towards that idea. It's pretty straight. It's also, did you all do your key terms and vocabulary yet for yesterday and today?
Yeah.
5 minutes a day. Okay. Let's look at number 23. Do we have that up?
Yeah, that's so calculate the Oh, we just did this question. It's just a different version.
Oh, okay, it's the same as 13?
Yeah.
Cool. Let's move on to 7.1 then. Good?
Yeah.
Cool. Let's move on to 7.1 then. I'm going to pause for a moment before we do 7.1 number 1 so I can help with the graph issues. If I could hit pause. Okay, so we're going to go ahead and look at the 7.1 questions if we want to start with number 1.
I don't think you have to go completely through. I think I'm just like forgetting something that I was supposed to
Let's see.
know. But it's, we burn 40 grams of iron to form Fe2O3. How much heat is given off?
Is that all the problem tells us?
That's it.
Whoa. No hints, nothing?
No.
Wow. I think I know what we're supposed to do.
I found how much, like, 40 grams of iron is
In moles.
of,
But that's not enough, right?
yeah.
So this is an example of kind of how information and hints kind of start to become less and less there, and it is kind of like the way that I frame these problems is we've got our right, we've got this kind of world, 40 grams iron goes to, right, that's all it gives us explicitly. And we want a result of energy, right? And someplace in between those things is all of this information. I frame the problems like this because I feel like everything in college and everything in life is kind of like this. We get some explicit information that's right in front of us. We've got someplace we want to end up. And someplace in between those two is all of this implied information that we're just supposed to know, right? In a course like this, I know what the implied information is. Depending on how much I'm expecting of the students, the implied information might be a really big gap or a really small gap. This is an example where the gap is really big. And when you get to your careers or your next stages of things you're doing, you run into situations where no one knows what the missing information in between is. So, in this situation, we have to figure out what that implied information is. And we look at this and we say, okay, so how do we get to some amount of kilojoules? It tells us we're burning this. So, must be a combustion reaction. No place does it tell us it's a combustion reaction, but it tells us it's burning, and we end up with iron oxide. So it must be iron plus O2 goes to Fe2O3. I'm going to need a 2, a 3, and a 4 to get that balanced. It's going to be solid, gas, solid. And I say, okay, with this, can I figure out how do I get to a kilojoules of energy released from a chemical reaction?
You have to use the
Yeah, I'm going to use a Q equals an N delta H of reaction. But it doesn't give me a delta H of reaction. How do I get a delta H of reaction? What's that?
The table.
The tables. I'm going to have to do delta H of reaction is equal to sum of delta H of formations of the products minus sum of delta H of formations of the reactants. Right? All of the information, like we know how to do all of these things. Problems in the past has said, no, use the tables, right? It gives us that kind of hint to kind of be like, hey, we're going to help you kind of think about what's missing here. This problem is just like, figure it out. And kind of doesn't give us any of those hints, so we have to kind of lean back on our information, our knowledge about this subject material, and really kind of takes, like, look at how much implied information there is versus what the problem has in the setup, right? It's expecting us to know a lot of things already.
I think I can, like,
Cool.
do the rest.
Should we look at number 9 then?
Yeah.
Questions about this before I erase? Okay, let's.
So number 9 is a like half balance or half reaction balancing.
Okay. I'm worried that's going to be one of the really hard ones. Let's see.
I don't think it is. I think I kind of just wasn't sure what to do. Okay, so if you have S2O3 2 minus aqueous plus OCl minus aqueous, and it goes to Cl minus aqueous plus S4O2 minus 6 aqueous.
S4?
S4O6 2 minus aqueous, and then it's in acidic conditions.
We're doing that tomorrow. This is one of the tricky ones.
So, okay. I think I was just having trouble when I was doing this, because I get like when you do like the adding the electrons, like you count the basic stuff like that. I was confused. So what do I do if it's like it's S2O3 and the other one is S4O6?
So this is also acidic conditions. We're going to be talking about this tomorrow in class.
You can like add oxygen. I watched a video about
it. So we got to do our half reactions. I'm going to go ahead and do OCl minus first. Sorry, that's not. Yeah, it goes to Cl minus.
Also for choosing like what what goes together in half reactions, I've just been doing with what looks alike.
Yeah,
is that
exactly.
fine? Okay.
Exactly. So I know that these are aqueous solutions, so I can go ahead and do a plus H2O. So I've got the right number of oxygens. I've already got the right number of chlorines. And then since it's acidic conditions, I can just do plus 2H plus to balance out the hydrogens. Now I have to make sure I'm charge balanced. I've got a -1, a -1, a +2. I also need 2 electrons. That's going to be that half balancing. Then I can do the same thing here with the S2O3, 2 minus, the S4O6, 2 minus. This one's actually a little bit easier than the first one. I thought the one I did first was going to be easier, because notice 4 and 6, 2 and 3, just put a 2 there.
Okay.
And now that's the right number of sulfurs, the right number of oxygens. But now I've got too much charge over here, so I just needed plus 2 electrons.
So if you have, so I think, this is where I got you. So if they have the same amount of electrons, then you don't need to multiply them or anything.
Correct. Then I can just put them together. And I'm going to get 2H plus OCl minus plus 2 S2O3 2 minus goes to S4O6 2 minus plus Cl minus plus H2O. I always like to double check at the end of that as well. So I've got 2 hydrogens, 1 oxygen, 1 oxygen, 1 chlorine, 1 chlorine, 4 sulfurs, 6 oxygens, 6 oxygens.
Okay. And then the other thing I was having trouble.
And yeah, that's a tricky one. We'll be learning more about that in class tomorrow.
Really?
Yeah.
I thought it was fun. I just got tripped up on the 2, on whether or not I need to put a 2 in front of it.
Oh, gotcha.
But okay, so this is like for a harder question. But like, so if you have, so when you have, like, say you have like 6 hydrogens there, and then you have like 4 hydrogens here. Like, how do you deal with, like, do you subtract them or do you just keep them the same? Or like,
if it was like
when
6
it's not-
H pluses
when it's
and
not
4
equal.
H pluses,
when it's not equal on both sides, like, how do you?
cancel out as many as you can.
But like, so which side do you like?
Whichever one. So let's say if for some reason we had like
Or should I just give you a problem? There's a problem with it.
let's say we got plus 8 and we've got plus 6H plus over here. We did something weird and we ended up with that. Well, I'm going to cancel out all 6 here, and this side that has more is just going to end up with 2H plus left over. So I cancel out as many as possible. So the smaller number completely goes away. The bigger number just leaves 1 or 2 behind.
And it doesn't matter which side it's on? Like if
It can go either direction.
Could
Yeah.
you, okay, so then could you go over one other problem, because then I don't
Yeah.
know what I took wrong. Okay, so this is question 12, and it's the same thing, like same instructions. And the question is, so.
Hold on, let me erase first.
Okay, yeah, sorry.
I have a question. About
Yeah.
Can you explain why you added the 2 electrons on this side?
So the reason I added the 2 electrons is because notice I've got 2 of these things, which is going to give me a -4 on my reactant side. I've only got a -2 on my product side. If I want to get it charge balanced, I need -4 on both sides.
Okay.
So 2 more electrons on over here is going to give me -2 plus another -2. That's -4 on this side. -2 here, -4 on this side. Okay. Other questions? Erasing. So let's go ahead. We're doing number 12, and then we'll do those post-lab questions as well. Number 12.
Okay, so this is, same, like, instructions, but the formula is I2 aqueous plus OCl minus aqueous goes to IO3 minus aqueous plus Cl minus aqueous. And then it's in acidic conditions. So when it's, sorry, quick question, but when it's in basic conditions, what do you just do the same thing and then you have to use OH
There's
minus?
just 2 extra steps if we're doing basic conditions. Acidic's not so bad. Basic is actually not that bad. There's just a weird trick to make it. There's like a hard way to do it and an easy way to do it. The easy way to do it has 2 extra steps, but you're less likely to make a mistake. Okay. I'm still kind of blown away by the weather today. In any case, we'll do the same thing. We're going to split it up into 2 halves. I'm going to put my iodine and my iodine together. So I'm going to have I2 going to IO3 minus. First thing I need to do is balance the iodine. So I'm going to just put a 2 there. So I've got 2 iodines, 2 iodines. It's going to give me 6 extra oxygens on my product side. So I'm going to have to add 6 H2Os to my reactant side. So I've got 6 oxygens, 6 oxygens. Then I've got 12 hydrogens. Since I'm specifically in acidic conditions, I've got H pluses, right? The reason I can add waters is because they're aqueous. There's just water floating around. But there's also acidic conditions, so I can just throw 12 H plus on here. And I've got a bunch of extra hydrogens. Now I have to do my charge balancing. I've got, this side is completely neutral. My net reactants are 0 charge, 0 charge. My products now need to total up to 0 charge. But I've got -2 plus 12, so I'm going to need 10 electrons over here. This means I can tell that the iodine...
In basic conditions, you wouldn't be able to do that, right?
Basic conditions, we're going to have 2 extra steps before we do that. We have to get rid of the H pluses with OH minuses. We'll do that a little bit later.
Okay.
But there's 2 extras. The first thing is you could try to just add OHs to balance the H2Os, but most people mess it up if they do it that way. So we've got this 2-step trick that we will look at a little bit later.
Where do the extra electrons come from?
Need,
Oh, okay.
right? So we know that electrons are transferring from one thing to another. I can tell that this is oxidized 2 ways, right? First off, electrons are lost, so it's oxidation. Also notice my iodine goes from no oxygen attached to oxygens attached. That's oxidized. So in this process of oxidizing, a bunch of electrons are kicked off. Now, those electrons can't float around on their own. This is why it's a half reaction. Now let's go ahead and look at what's happening with the OCl part of it. So that's going to be OCl. This is the same one we just did. Cl minus plus H2O to get my oxygens balanced, because there's water floating around, plus 2H plus to get my hydrogens balanced, plus 2 electrons to get my electrons balanced. Now, my electrons are balanced in the reaction. In the half reactions, my charge is balanced in the half reactions, but my electrons are not overall balanced, right? I've got 10 electrons being produced, but only 2 being used. So that means this reaction has to be 5x'd. Every one time this iodine thing happens, this chloride, hypochlorite thing needs to happen 5 times. Now I can put this together into my overall, and I'm going to do it a little bit different than last time. I'm going to have 10 electrons, because it's 5 times that, plus 10H plus 5 OCl minus, so that's my 5 times all of that, plus 6 H2O, plus I2, and I don't have enough space, so I'm going to go this direction. Don't mind me.
Wait, why'd you multiply it by 5?
Because I only have 2 electrons, and I have 10 electrons, and I need them to match.
Okay.
And dividing this one by 5 would be weird, multiplying this one by 5, because I'd end up with half coefficients, and I don't like that. It looks weird to me. So then we can go ahead and look at this and say, okay, on the product side, I'm going to have 5 Cl minus plus 5 H2O plus 2 IO3 minus plus 12 H plus 10 electrons. And that's right there is the important thing, right? My electrons have to be complete. I can't have electrons floating around willy-nilly, so my electrons perfectly cancel out. That's really important. That was the whole reason we did the multiply by 5. In terms of other things that cancel out, I've got 10H plus and 12 there, so that's going to leave me with 2H plus left over there. I've also got 5H2O. That's going to leave me with just 1 H2O on my product side. And everything else looks good. So my final overall reaction is going to be 5Cl minus. Whoa, sorry, writing the wrong thing. My final overall reaction is going to be 5OCl minus plus I2 plus H2O goes to 5Cl minus plus 2 IO3 minus plus 2H plus. I'm going to double check because it's very easy to lose track of things when I'm trying to do this quickly. And there's so many steps, it's easy to lose track of things. I've got 5 chlorines, I've got 2 iodine, 2 iodine. I've got 1, 2, I've got 5, 6 oxygens, I've got 6 oxygens, that's looking good. I've got 2 hydrogens, I've got 2 hydrogens, it looks good.
That's what I have, and it's wrong.
10 electrons transferred. Let's take a look. My guess is you've got a weird typo someplace. May I take a look? Yeah. Okay, let's see here. H2O liquid plus I2 aqueous plus 5 OCl aqueous. You forgot your H2O.
No, it's
Oh no, it's in the front. Okay. What is going on here?
And I don't think I've messed up the states either.
I don't think so. I was being lazy with the states. Do you have it as H plus or H3O plus? H plus, okay. Sometimes that's a thing. 5HCl, 2H plus, 2IO3 minus. Why is this?
It might just be like a capitalization thing or something.
I think it is. I'm trying to find it. That's usually what it is. The two common mistakes that happen, there's a few things that can go wrong that totally are difficult to see. One is zeros instead of O's. Oh, I see it. You put your coefficients in with the formula rather than the coefficients in the coefficient boxes. That's all.
Okay.
So you did it totally right, and you just like syntax errors.
Could you go over how to do like a base one in basic? Should I give you a problem?
No, let's just pretend like this one's in So how would this be different if we did it in basic conditions? Again, we're going to do this tomorrow in class, but I like getting ahead on things, so this is totally fine to do. Let's just go back to the very beginning of this. I should have asked, is it okay if I erase everything? Everyone okay with that? And let's just do one switch. Let's just say what would happen if this was, instead of acidic, what if this was in basic conditions? Right, it's gonna start pretty much. I'm gonna do the OCl one first, just for fun. So we're gonna have OCl minus going to Cl minus, and it starts the same way, where I add H2O to balance out my oxygens. And then I do a little crafty thing of I add H plus, I add 2 H plus to balance the hydrogens, and then I add 2 OH minuses to both sides. And the reason I do that is because I can't actually add H plus, but I know if I add H plus and OH minuses in equal amounts, that just makes H2Os, right, through neutralization. And so it gives me this kind of like quick way to keep track of my hydrogens and oxygens with waters. So if I just tried to go straight to adding OH minuses here, I would probably mess up. Because the OH minuses, I'm going to switch which side needs water to balance the oxygens, because if I add 2 OH minuses here, now I've got too many oxygens, so I have to like add another water over there. But if I add the water, now I've got extra hydrogens, and I have to balance the right number of hydrogens to the right number of oxygens. So I do it this way, and it turns out the OH minuses actually ended up on the other side. So then I end up with 2 H2O plus OCl minus goes to Cl minus plus H2O plus 2 OH minus. And I can get rid of this H2O and one of those H2Os. So at first glance, it looked like I needed to add water to the product side to balance my oxygens. But because of the way that hydroxide plays a role, I actually needed 1 water on the reactant side and 2 hydroxides on the product side. And for me, I would have never guessed that if I didn't do this hydrogen hydroxide trick. So the hydrogen hydroxide trick is this nice little like neutralization process. So I have this easy stepwise way to figure out where the hydroxides actually go.
So that's just the only thing that's different.
That's the only thing that's different is this one extra step. It's kind of 2 because you add hydroxides to both sides and then you got to cancel the extra waters. And so that's the 2 extra steps. And that's it. And it's the same thing. Question?
Can I ask about how you calculate on the equilibrium lab?
Yeah, is this particular to your data? Or is it one of the post-lab questions?
No, it's just like how exactly you calculate it.
Sure. Let me do these 2 questions because it might be like a particular thing with your data to look at. So let's do the post-lab questions 2 and 3, and then I'll help you out with that if that's okay. Okay if I erase this? We didn't finish the problem, that was just a little bit of an example.
Do we have enough time to go over another thing?
Sure.
I just wanted to go
Let's
over,
get these
yeah,
2,
after, like,
that question, and then we'll do some other things. But I think we got time. I lost track of time, I don't know.
It's almost
It's 3:30.
Yeah, we got plenty of time. We got like 30 minutes still.
So
Post-lab number 2?
yes, so at 450 degrees Celsius, ammonia gas decomposes according to the following equation. 2NH3 gas turns into N2 gas plus 3H2 gas with a Kc of 6.3 at 450 degrees Celsius.
6.3?
Yeah.
Great.
And then an unknown quantity of NH3 is placed in a reaction flask with no N2 or H2 and is allowed to come to equilibrium at 450 degrees Celsius. The equilibrium concentration of H2 is then determined to be 0.149 moles, or molarity. Determine the initial concentration of NH3 placed in a flask.
How is this even possible? I'm teasing. This is backwards from what we usually do.
Okay.
Right? So, and you'll notice I've got particular subscripts to keep track of things here. So I'm going to go ahead, and I like to use question mark because if I use X for everything, I get confused. So I'm going to go ahead and write down my balanced chemical equation again. I'm going to have NH3, 2NH3, going through equilibrium to N2. I'm going to have my initial, my change, my equilibrium is still an equilibrium problem, just like always. My NH3 is an unknown quantity. I'm going to use question mark because I'm going to have too many X's otherwise. And that's the only thing I put in. So those are going to start as zeros. I'm going to have minus 2x plus x plus 3x. I'm going to have question mark minus 2x. I'm going to have x. I'm going to have 3x. And if that was all the information we had, this is going to be impossible because I've got 2 equations, 2 unknowns. I'm going to have this set up. Sorry, 1 equation, 2 unknowns. I'm going to have Kc is equal to products over reactants, 3x cubed times x divided by question mark minus x. Sorry, minus 2x. Right? How could I possibly solve this? Where's the extra bit of information that we have that lets us solve this? Yes, that helps, but there's one more really important piece of information. Yeah, right? This H2 concentration is 3x. So that means I can solve x is equal to 0.149 divided by 3, and then I can plug in all of those x values.
Okay.
Right? And it's one of those things where it looks really easy now, right? How much time did you spend staring at that, working on it?
A little too long.
Right. And so this is people always get mad at me for not having answer keys. This is why I don't have answer keys. Right? If you can flip and look at the answer, you have that moment where you're like, "Oh, so easy." But like you're going to know how to do this in the future now because you put so much work into it. Even though a lot of that work feels like frivolous or not useful because you couldn't figure it out, that struggling process is going to make this stick in your memory better. And so if you see a problem like that, you're going to be like, let me check this other thing that I totally spent too much time figuring out before. So it's going to be really useful. So at that point, we can solve for x, and then we can just plug everything in. Let's go ahead and do that. Hey, are you here for questions or just?
For my test.
Cool. Give me just a moment. So we can go ahead and do 0.149 divided by 3. That gets us 4.96. So then I can do, this is going to be 6.3 is equal to 0.149 cubed times 0.0496 divided by question mark minus 0.0993 squared.
Is the squared supposed to be also on the bottom?
Yeah.
Okay.
Yeah, I forgot it over there. I was just trying to think of easier ways. It's going to be fine. I was worried we're going to have to do a quadratic or something.
Okay.
But we're not.
No.
Right? So I'm just going to rearrange. I'm going to have question mark minus 0.0993 squared is equal to 0.149 cubed times 0.0496 divided by 6.3. I can just, since these are all numbers, I can just take the square root of that number and I don't have to do a quadratic.
Perfect.
Let me pause this real one. Okay, so we got a couple questions from 6.2. We're looking at number 3, and then we got a conceptual question for 1314. I'm going to erase all of this. I think we're done with it. We haven't done post-lab number 3 yet. We might not need to because it was really similar to number 2, and it's kind of an initial acid problem. Okay, what is 6.2 number 3?
It says answer the following questions for the solution formed when 13.96 grams of NH4Cl solid is dissolved in 3,400 milliliters of water. It's asking for the total concentration of them.
Okay. What's it asking for the total concentration of?
Of cations, anions, the molar concentration, and the total concentration of all solids.
So it's asking for the concentration of NH4+. It's asking for the concentration of Cl-. It was also asking for
the molar concentration of the solution, and then the total concentration of all solute particles.
total concentration, molar concentration of the solution, total concentration of all solid. Interesting. That's a weird way to ask that question. So the first write down a piece of paper. Okay, so that's got some weird phrasing in it. I did not write this problem, but that's okay. So looking at this, ammonium chloride, when I looked at this, I was instantly thinking like, oh, it's going to be some weird like KSP problem. But ammonium chloride is incredibly soluble. I don't think we even need to do an equilibrium table. We could check trying to look up the ammonium chloride KSP value, but I'm willing to bet we won't find it because it's like billions. So we can just do, to get the cation anion, we can start with just recognizing that it's going to be NH4Cl, solid, going to NH4 plus Cl minus. I need to figure out the molarity. I need to figure out the moles per liter. So I need to figure out the moles of each thing. So I'm going to take my 13.96 grams. I'm going to multiply by 1 mole. Has the molecular weight, nitrogen, hydrogen, chlorine. Why do I keep losing my calculators? That's okay. I've got like 5 around here. That's why it's funny I keep losing them. So that's going to be 35.45 plus 4 plus 14. So 53.45. Inverse times 13.96. So we're going to have 0.261 moles. And it's going to break into 0.216 moles and 0.216 moles. Assuming reaction is incredibly soluble. That allows me to just take both of those.
216 or is it the same?
261,
Okay.
sorry, 261. 261, yeah. So I'm going to do 0.261 divided by 3.4 liters. That's just me doing that conversion. Divided by 3.4. And I'm going to get a concentration of 0.0768 molarity.
So that's for molar concentrations.
Well, that should be the molarity of the, I think that's going to be like 3 of the numbers, right? So that's going to be the molar, so that's going to be the concentration of NH4 plus in solution, the concentration of Cl minus in solution, for sure. And then if I add those two numbers together, that should get the total molarity. Total molar concentration is the one that I feel like, or like the molar concentration of the solution is the one that's kind of weirding me out. Let me check something real quick. Okay, so you got actually a fortunate one because we got a nice 1-to-1 mole ratio. This problem is randomized where there's a lot of different options. And for the 1-to-1 mole ratio, it's pretty easy to see that, like, you know, this 0.768, that is going to be equal to the NH3 the NH4 plus concentration. That's going to be equal to the Cl minus concentration, and it's going to be equal to the then the total concentration is just going to be the concentration of NH4 plus the concentration of Cl minus. The place where it gets strange is if we had something that wasn't a 1-to-1 mole ratio. If we had something that was like a 2-to-1 mole ratio, then we'd have to plug in and figure out, you know, it'd be like 0.768 and like double that if it was like magnesium chloride instead. And then that would change the total concentration and the molar concentration and kind of shift everything a little bit. And the molar concentration would be related to like the molar concentration of the solid. So if it was magnesium chloride, MgCl2, it would be the 1 ratio to the solid, not the 2 ratio to the solid. Weird problem. It's just using, so it's it was weird for 2 reasons. One, I have a hunch for who coded it because I recognize like code is like fingerprints, and I'm like, oh, I bet I know who wrote this problem. I did not write this problem. I code a little, my style of coding is just a little different. It took me a while to kind of like untangle it, but it was the molar concentration. I call this, when I'm talking about the molar concentration of the solid dissolved, I use a little bit different vocabulary for that. I call it molar solubility. I would specifically call it molar solubility of the solid, just to remove that ambiguity. Did it work?
Yes.
Awesome! Okay, see ya. Let's go ahead and, what's your concept question for 1314?
So it's for.
Is it okay if I erase all this? We're all good?
It's just like describing what the reducing agent is and then it being oxidized versus the oxidizing agent and it being reduced. Like I feel like I knew like in the past what this meant, but it's not clicking anymore.
Okay. Now, this is for me, it's still frustration, right? And it has to do with this whole, like, how was this originally understood versus how do we use it now? And so we talked about this in class yesterday, And for me, the easiest thing to think about is iron solid reacting with O2 gas to form iron oxide. 2, 3, 4. Right, so this is iron oxide getting iron getting oxidized into iron oxide. It's rust. It's iron turning into rust. And the way that I remember it is oxygen right? Oxygen is acting as the oxidizing agent causing iron to get oxidized. Right, and so this is, the reason I like this as a first example is because this kind of shows you where that language comes from. Right, oxygen, right, it feels funny to call oxygen an oxidizing agent because it's oxygen. But the problem is we have things that behave like oxidizing agents besides oxygen. So oxygen is causing something else. The agent is causing something to happen to something else. Oxygen is causing iron to get oxidized, which means it's the thing causing that oxidation to happen. But in order to cause that, it's getting reduced. Oxygen is pulling electrons towards it, which means it's getting reduced, but it's pulling electrons away from iron. So it's the oxidizing agent causing iron to get oxidized, causing iron to lose its oxygens. Right? And so I think about it this is the one that I have to go to for my conceptual thinking. Oxygen is the oxidizing agent causing iron to get oxidized. It's Wednesday. I totally forgot about a student meeting earlier today. It's Wednesday. Oh man.
It's cool.
I
I also have concept questions.
No, this is a different entirely thing. Sorry, I shouldn't have recorded that. Apologies. I just realized because I started. Never mind. It's fine. And then reducing agent is the opposite, right? So in this situation, iron getting oxidized is giving its electrons away to oxygen. So it's the reducing agent causing oxygen to get reduced. Right? So the problem with the language here is it was originally all done in terms of where's oxygen coming from and going to, rather than where the electrons are coming from and going to, which causes us to need this translation of the reducing agent is getting oxidized. The oxidizing agent is getting reduced.
So oxygen's not always the one being oxidized. It could also be reduced if it's losing electrons?
It could.
Okay.
That's a little unusual.
Okay.
And the reason it's a little unusual, we'll see when we start to, is because of the reduction potentials. Oxygen's reduction potential is pretty high. It's pretty good at
It's pretty good at losing electrons.
gaining
Gaining
electrons.
right.
It's pretty good at gaining electrons. There are things that are better than oxygen at gaining electrons, but not many.
Yeah, there was a question at the bottom. I was gonna say that because it was one of the it doesn't give feedback as a graded question. It was like I think it was magnesium and oxygen or something, and then it was like oxygen. I think I put as the one that was reduced instead or something.
Yeah, that makes sense.
Okay. Okay, perfect.
Cool. Is that good?
Yeah.
So
Cool.
much.
Okay, I'm gonna go ahead and stop recording. I'm going to post these right now. So if you need to